We've introduced how to solve a system of differential equations, that is, first-order differential equations. They're in the form x prime equals a times x. Our three steps are this. We find the eigenvalues, and we do this by setting the determinant of a minus ri equal to 0. Since we have two equations, that is, we have an x and a y, a 2 by 2 matrix that is for a, we should have two solutions for r. Once we have our two r values, we find the corresponding eigenvector for each of those eigenvalues. And we do that by using the formula a minus ri times this vector u, which is our eigenvector, equals the 0 vector. And finally, we build the solution. This should remind you a little bit of when we were doing characteristic equations, that when we had a second order differential equations and we solved for r, we had again two solutions. We had three different kinds of solutions. We had either two distinct real, one repeated real, or two complex values for r. In the previous video, I did an example with two real distinct solutions for r. When we found our two values for r and our two eigenvectors, our general solution for two distinct real is always in the form of c1 e to the r1t times eigenvector u1 plus c2 e to the r2t eigenvector u2. Now notice if we had three solutions, say we had a 3 by 3 matrix, it would still be in this exact same. But for exams, we're going to stick with a 2 by 2 matrix. Therefore, your solutions will always look like this if we have two distinct real. So now we have to talk about what happens if we get one repeated real solution and what happens if we get two complex. The repeated real solution is a little bit trickier than when we dealt with second order differential equations. If you recall, all we ended up doing was throwing an extra t at it. What we have to do in the case of a system of differential equations, however, it's a little bit more complex. In this video, we're going to focus on what happens when you have the repeated real. That is a repeated real with multiplicity of 2. That is, it's repeated twice. There are special cases where you have symmetric matrices that you're not going to have to do this. But in general, those matrices are not as common, so we're always going to be using this method. What we're going to do is say, as before, we're going to set this up like we have in the past. X is going to be equal to c1 times our first solution x1 plus c2 times our second solution x2. x1 is going to be set up just like we did for the two distinct real solutions. So to find the first solution, we take that r, which we found by setting the determinant of a minus ri equal to 0, and in this case we'll only have one value for r. And then we'll find an eigenvector associated with that value r, the eigenvalue r, just like we did before. That is a minus ri times my eigenvector u1 equals 0. The question is, how do we come up with a independent u2? We don't want a linearly dependent u2, because if we recall from before, we need our x1 and our x2 to be independent in order for it to be the full solution. So what we're going to do is one small change. Well, I take that back, two small changes. The first part of my x2 is going to simply be, like we did with second order differential equations, that original solution with a t thrown at it. However, now we've got the second eigenvector u2. How do we find that? Well, instead of having our equation equaling 0, we're going to have it equal u1. So this is a little bit different. It's so easy to make mistakes with this. I'm going to give what's colored in purple on the exam. So there will be a formula sheet with these formulas on it, and it will specifically say for repeated eigenvalues with multiplicity of 2. And let's go through an example of that. Before I do, I want to go back to what we talked about here, our general steps, and I want to add one. If I give you initial conditions, then those initial conditions can be used to find C1 and C2. That will be true whether we have two distinct real, one repeated real, or two complex solutions. So let's do an example of this from start to finish. Here's the problem: x prime equals the matrix 1, negative 1, 4, negative 3 times x. So let's go ahead and first of all find our eigenvalues. Again, we do that by taking the determinant of a minus ri and setting that equal to 0. Remember, to take the determinant, we multiply those two items from the first diagonal, and then subtract those two multiplied together from the second diagonal. I forgot my second negative r, so now let's go ahead and multiply that out. When we multiply this out and collect like terms, we get r squared plus 2r plus 1. If I go ahead and factor this, I get r plus 1 squared. I end up with an eigenvalue of -1, and that's repeated with a multiplicity of 2. So let's go ahead and find our first eigenvector. This is how I set it up, and when I go ahead and do my addition, I get this. In this case, I think it's very easy to see that the first row and the second row are in fact linearly dependent. If I took the first row and multiplied it by 2, I would get the second row. So it doesn't matter which of these rows I use, but I usually use the first one. Let's go ahead and find the relationship between u1 and u2. When I multiply the 2, -1 times the u1, u2, this is the equation I get. And then this leads to the following eigenvector. Remember, you always end up swapping the coefficients, because if I plug in 1 for u1, 2 times u1, or 2 times 1 would be 2, and that would lead to the value I have for u2. So this is my first eigenvector, but I need a second eigenvector. And the second eigenvector I find by setting this equation equal to the eigenvector I just found, u1. Here I've gone ahead and set up the matrices, and when I multiply it out, I get the following. So this isn't as nice as it was before. I can't get u1 and u2 by themselves on either side of the equal sign because of the +1. But remember, there's an infinite number of eigenvectors associated with an eigenvalue. So what I'm going to do is, in order to preserve the relationship between u1 and u2, I'm going to pick a value, say for u2, and I'm going to solve for u1. My favorite number to pick is 0, because that makes things much easier. If u1 is equal to 0, that means u2 is simply equal to -1. So my second eigenvector is simply 0, -1. I could have picked 0 for u2, in which case u1 would have equaled 1/2. As long as I have the correct relationship between u1 and u2, it's a correct answer. And again, my constant would take care of this at the end when I put it all together. Let's put my solution together. First x1, this is my value for x1, and then finally x2. And here is my x2. Finally, my x is simply equal to c1 times x1 plus c2 times this entire x2, and that is my final answer. So this is an example of a repeated real eigenvalue.